Right, hi everyone, and welcome to this week's Cambridge Zero Research Symposium. I'm going to get started, but I know people are still filtering in, and there's a few minutes here of introduction, so to give everyone else a chance to join in. But today's Research Symposium is on the topic of carbon drawdown and climate repair, and we've got a great lineup of speakers for you all today. So I'll just quickly introduce them here, but I'll let each of the speakers obviously introduce their own slides as they come up. So our keynote speakers today are Dr. Hugh Hunt from the Centre for Climate Repair in the Department of Engineering. He'll be speaking on going further than net zero. Then we have Dr. Marek from the Department of Chemical Engineering and Biotechnology, speaking on looping oxygen to capture carbon. Professor David Coomes will be from the Department of Applied Sciences, is speaking on planting trees to save the planet, greenwashing or golden opportunity. Then we've got 6 early career and postgraduate researchers also presenting today. Dr. Zeynep Clulow from the Energy Policy Research Group in the Judge Business School will be speaking on the socio-economic and political challenges to negative emissions technologies. Dr. Paul Griffiths from the Chemistry Department on quantifying radiative forcing impacts of a shift to a hydrogen economy using a chemistry climate model. Dr. Quigley from the Centre for the Study of Existential Risk will be speaking on how to decarbonise the financial system. James Weber from the Chemistry Department as well on minimal climate impacts from short-lived climate forces following emissions reductions related to the COVID-19 pandemic. Michael Glerum from the Engineering Department on production of advanced carbon nanomaterials. And finally, we've got Sam Gabra from Chemical Engineering and Biotechnology, who will be speaking on chemicals production. Can it be more environmentally friendly? So that's our program for today. I'll just quickly run through the Q&A rules. So after each of the presentations, there will be an opportunity to ask questions. Please do submit your questions through the Q&A box on Zoom. You can find that in the bottom bar on your screen. You can submit questions at any point during talks or also after the talks, but please address them to the speaker you are asking the question of, so that we know who you want to answer. You can upvote questions so that they come to the top of the Q&A box if you want to see those questions answered. And if we run out of time to answer all the questions live, there is the opportunity for speakers to type answers to questions directly into the Q&A box so that we can carry on with the next presentations. So you just use the type answer function within the Q&A box to do that. I should also say that this session is being recorded, and we will share the recording of this session on YouTube afterwards. Then just to say quickly that this is the final one of our 6 research symposia in the series we've had this term. So you can see the other 5 that we've already had over the past few weeks, and recordings of all those research symposia are available on our website. Follow the link at the bottom there, and we will share that link with you afterwards. And I just want to highlight a few more events that are coming up this week. So it's quite a busy week. Tomorrow, we've got the climate change lecture series kicking off, which Hugh Hunt is also directly involved in. And so please do register for that at the climateseries.com website. And then on Friday, Energy Transitions are holding the next installment of their discussion series on photovoltaics. So please join that as well. We have various events later this month in the Cambridge Festival on the 26th and the 27th of March. So please join those events too. Also, a final reminder that the submissions are still open for Climate Expo. This is our big virtual conference that we're running together with the COP26 Universities Network. And if you want to submit an abstract to that conference, please do so today, because today is the deadline. And finally, do sign up to our mailing list and our Twitter and LinkedIn pages, and those links will be shared with everyone after today's session as well. So I'm going to stop there. I hope that everyone's had a chance to get into the call now. I see we've got lots of attendees here, and I'll stop sharing my screen and then hand over to our first speaker, Hugh Hunt. So over to you, Hugh, and please share your screen. And I think you're still muted, Hugh. Just need to unmute.
I'm sharing the screen.
Yeah, okay, so we had your screen, now we've lost it again.
I know, I just couldn't find the...
Okay. There we go. That's it.
Well, thank you very much for inviting me to speak on this, this subject, carbon drawdown and climate repair. The Centre for Climate Repair is a new thing in Cambridge, and we're very glad to be looking into some of the issues related to removing carbon dioxide from the atmosphere and controlling the climate. Now, the Paris Agreement dealt with carbon drawdown. It didn't say it in those words, but it does aim to limit warming to 1.5 degrees and achieve a climate neutral world by mid-century. And that kind of, the word neutral is where the net zero carbon drawdown message comes in. Now, COP23, I was there and I found it rather interesting because the Fijians, who were ostensibly hosting COP23, although it was held in Germany, went to see a coal mine. And this was the scale that they just hadn't imagined that they saw before them. Now, this is a small coal mine on the grand scheme of things, perhaps 0.4% of global production. We've really got to stop burning fossil fuels. That's just clear. But greenhouse gas levels continue to rise. The CO2 levels at the moment are around 415, 20 parts per million, including non-CO2 greenhouse gases, perhaps up closer to 500. Now, the dot on the left is where things were around 100 years ago, around World War I. And that's when the temperatures in the planet were pretty genteel, really, lots of bluish and sort of pale colors. But 100 years later, the temperatures have got a lot hotter, particularly up around in the Arctic. And it's the Arctic that is giving us cause for concern. So what is the Arctic problem? The first one is that the ice floating around in the Arctic is nice and reflective. And when you lose the ice and you get open water, the reflectivity or the albedo drops from 60% reflectivity down to about 10%. And this is reckoned to have an effect equivalent to about 25 years of our emissions. Now, the ice is melting, and okay, every time we see pictures of the Arctic, we still see ice. But if we can't kind of visualize it, just imagine this is your gin and tonic or your glass of soda water. If you've got ice floating in it, you know that it's cold. But as the ice drops down a bit, you're worried that, oh, well, soon the ice will all be gone and my drink will warm up. Well, that's the situation we are currently facing in the Arctic. That's the situation 3 years ago. The ice is almost all gone. Now, we've got to make sure that doesn't happen. It really mustn't happen. Because we know that if we lose the Arctic ice, then there's the likelihood of release of methane. Methane is a 20 to 80 times more potent greenhouse gas than CO2. And methane release has been known to be doing pretty strange things. These explosive releases up in Siberia are pretty exciting. The two circled regions are on the far side of this crater are some people standing having a look. And you can see the shadow of the person taking the photograph. These are huge craters caused by, well, organic material in the permafrost beginning to decay and release. We also know that if the Greenland ice shelf melts, it holds a couple of million cubic kilometers of ice. That would lead to, if it all melted, that's 7 meters of sea level rise around the world. And we're already dealing with sea level rise. This is a picture just taken last month in Jakarta. And we know that we've seen strange weather patterns caused by, well, the warming Arctic is destabilizing the weather. Well, we ought to be doing something by reducing emissions. But if we look at how well this, call it Plan A, is working, fossil fuel emissions are rising. This is showing percentage increase since the year 2000. So 50% rise since then on fossil fuel in use globally. You might say that's due to population growth. Well, yes, population has gone up, but energy use per population is also going up. Well, why is that? Surely we're getting good at solar and wind and energy efficiency. But in fact, that's not happening. And carbon dioxide use per unit energy isn't really changing very much. We're relying on technology, and it just isn't working for us. So we have to think a little bit about what might our plan B be. Now, perhaps we should be reducing our emissions, take personal responsibility for these things. I like to think, though, that if global emissions are about 35 billion tons of CO2, and there's about 7 billion people on the planet. It's a nice sum to do, 35 divided by 7. Each individual on average is responsible for 5 tons per person per year of CO2. And that's been rising, as you can see in this graph. And we've got to come down on the other side to get really down to zero pretty soon. But what is my responsibility? The thing is that we tend to think of our responsibility of things like the garbage we put out or the stuff we flush down the toilet. But I reckon for my household, that's about 500 kilograms per year. So 5 tons a year is rather a lot, isn't it? But we don't tend to think that way. If I'm flying to see my family and friends in Melbourne, where I grew up, I get to the airport and maybe I might scratch my head and think, well, where's the CO2? So I have to do a calculation. I imagine that this suitcase contains 20 kilograms of carbon dioxide. And I want to know how many of these suitcases do I need to pick up at the airport in Melbourne when I arrive, which is my personal contribution. Well, the calculation, I can look up how much fuel the plane burns per second, and I know it's a 20-hour flight, and I know that there's about 350 passengers, and each kilogram of fuel generates about 3 kilograms of CO2. That's actually enough information for me to do a calculation on how many suitcases I should pick up at Melbourne Airport when I arrive. And the answer is 125 of them. And that's just me. And that's one way. Return trip, 5 tons, 250 suitcases. And that is the entirety of an average person's CO2 emissions at present, based on global emissions. And we've got to reduce that. But of course, when I get to the airport, this is what I see, and I'm annoyed that my baggage isn't coming out. The CO2 is the last thing that's on my mind. So we're going to struggle to be changing our emissions as individuals in the near future. It's not going to happen very fast. So what are we doing by nations? Well, COP26 is coming up, and the idea is that COP26 is intended to improve on and to check the progress of these nationally determined contributions that were fixed in a COP21 in Paris 5 years ago, or 6 years ago now. The baseline, as you can see, is rising. There is current policy trajectory, which is not much lower than the baseline. And then there are this sort of, well, scratch our heads, what is it that countries are willing to do? Well, there's not much willingness to do anything. We've got to follow these two curves down, 2 degrees, 1.5 degrees, in order to get to, well, even they don't get us to zero in 2050. So what we need to do is to think about negative emissions or carbon drawdown. There's lots of different names for these things. Now, this shows the same old graph of our annual emissions, gigatons, billion tons of CO2, rising up to 50 or 55 billion tons per year around now. And there's a business as usual line. And then there's a few lines below this trying to get us down to net zero. Well, net zero includes this blue bit at the bottom, which are carbon removal technologies that account for the fact that our mitigated emissions, that is trying to use as much wind turbines and solar power and nuclear as possible, that doesn't do enough. We still have residual CO2 emissions from things we can't avoid. Maybe we say we can't avoid flying, or we can't avoid steel or shipping. Well, the red dotted line is really where we need to follow to get down to be actually net zero by 2050. So even this diagram doesn't show particularly great ambition. it's pretty clear we're going to need to do a lot of weird and wonderful things at scale and pretty quickly. So let's think about carbon drawdown. There was a project I was involved in about 10 years ago, integrated assessment of geoengineering proposals. And in it talked about things like biomass energy with carbon capture and storage. Well, that's kind of established now that we plant trees and then we feed them to power stations. The Drax power station in the north of England, well, that's the biggest one in the world at the moment. It's pretty amazing. The idea is that this power station, represented by what looks like a house in the middle, doesn't have a chimney. Instead, it puts its CO2 directly underground. That is negative emissions because the trees suck up the CO2 and we put it underground. And believe it or not, the Paris Agreement doesn't say it in words, but we cannot achieve the Paris goals without negative emissions like this. But there are other greenhouse gas removal technologies. We can fertilize the oceans, we can grow trees and then spread the trees as biochar into the soil, or even just planting lots of trees. Maybe that's enough, but we can perhaps look at enhanced weathering of rocks, or we can look at ambient air capture of CO2. All of these are carbon dioxide removal techniques. We can look at other so-called geoengineering proposals. The word geoengineering won't go away, I'm afraid. Solar reflectivity management or solar radiation management, whatever you'd like to call that acronym. The idea that you can make the ground whiter, make the sea whiter, make clouds whiter, put particles up in the stratosphere to reflect sunlight, all these kinds of things. Rather scary, but these technologies are, well, perhaps affordable and are perhaps achievable in the near future. We really ought to be doing research into these technologies. Here are some examples in more detail. Direct air capture. Ava will talk a bit about this later on. The idea is that we can use, hopefully, solar or wind energy to capture CO2 from the air. My worry is that we might end up using this technology just to make synthetic fuel so that we can carry on flying. And I really don't think we ought to be flying very much if we can help it. We want to improve our ocean health. We know that. David Attenborough tells us that. And giant kelp, if we can make it grow faster and more of it, will help us capture and store CO2. And perhaps we can use it as alternative feed for cattle for those who still want to carry on eating beef. Ocean ion fertilization is a very interesting area. How can we encourage growth of phytoplankton, and the dead plankton will sink very deep and essentially stay there for hundreds of thousands of years. Increase soil carbon. Well, we really want to get our soils back to how perhaps they once were, so that we have reduced emissions. We want to avoid using nitrogen-based fertilizers, putting biochar, putting captured biomass into the soils has got to be a good thing. Solar radiation management, as I mentioned before, is a controversial thing, but the research needs to be done. We just don't know where we will be in the next 5 or 10 years. Desperate times may need desperate measures. But what's very clear is that certainly in the Arctic, we've got to try and maintain the Arctic ice. Another technique that we're very interested in the moment is marine cloud brightening. The picture on the left shows tracks from shipping. And we see that when ships emit particles from their chimneys, that clouds are formed. So can we artificially create clouds? Now, all of this is great, but it's not just about the science. And the Centre for Climate Repair is very interested in the science, but also interested in governance and legality, license to operate, public opinion, economics, finance, scalability, and of course, safety and unintended consequences. So that's my little overview of carbon drawdown and climate repair, and I'd be happy to answer any questions.
Great, thank you very much, Hugh, for a really interesting talk and a good introduction to today's session. So I would like to invite any questions for Hugh now to come in through the Q&A. So if you have a question, please do ask that now. We've already got one question here coming from Herbert Hoopert. So he's saying, nice talk, interestingly presented, but you must be wrong. I hear always from industry that they're moving towards zero carbon in 2050. Even politicians say this. Aren't we well on the way? I guess your slides earlier showed that we aren't well on the way, but do you want to add any more to that?
Well, I'd like to think we're well on the way, but I think our ambition has got to be far greater, because the hardest bit, I mean, the easy bit ought to be now. The hardest bit will be the last bit. It's like running a marathon. You know, the first, not that I've ever tried, but the first 10 miles, you know, you think, oh, this is great, no problem. But to achieve what we need to achieve by 2050 is going to be a marathon target, a marathon ask. And I don't think that we quite realize the sheer scale of it. And that's the problem, Herbert.
Right. Thank you, Hugh. There's another question here coming about explain cryovolcanism. I don't know if that's something I don't think that's something you mentioned, but is there something you want to add anything on, Hugh?
Well, yes, to be honest, I don't think there are clear explanations. This is the picture that I showed earlier of the blowing up. Let me just rather inelegantly go back to the picture. It looks like, well, these craters that appear, and many of them are filled up with water, and it's hard to know whether they're increasing in number and frequency, but it seems to be that the organic matter that's locked up in ice at the moment is warming up and is able to decompose. And the decomposing matter is producing methane and carbon dioxide, building up pressure. And when that pressure reaches a certain level, it explodes a mass of stuff out of the ground. And then after not too long, it fills up with water and just ends up looking like a lake. The real worry is that this so-called cryovolcanism, which is the name which has been coined recently, is on the increase on account of warming of the Arctic.
Great, thank you. Sorry, I hadn't seen that word cryovolcanism come up on the slide, but yes. Another question here from Nathan Jamieson saying, do you think that there's not been enough emphasis on BECCS, as this is what a lot of models use to achieve 2 degrees C?
Well, it's really interesting, the idea of BECCS, bioenergy with carbon capture and storage. It sounds great. It sounds like, oh, let's not burn coal and oil and natural gas in our power stations. Let's grow trees.
Oh, I seem to have lost Hugh, or is it just me who can't hear him anymore?
Yeah, we've lost him.
Yeah, we've lost him.
Okay, right. Let's give Hugh a chance to get back onto the call. And in the meantime, and we'll keep his questions coming up in the Q&A. In the meantime, we can move on to our next speaker then. So our next speaker, although, hang on, let me just stop the record. No. Can I stop Hugh's screen share? Sorry, just trying to stop Hugh's screen share. Okay, right, there we go. I think, so let's move on to our next speaker now. So Eva Marek from the Chemical Engineering and Biotechnology Department. Eva, over to you, and please share your screen.
So that was kind of surprising, unexpected, but I were to talk one way or another, right? So you see my screen okay?
Yes, we can see your screen, great.
Great, so hello everyone, my name is Eva Marek. I'm from Energy Reaction and Carriers Group from the Chemical Engineering and Biotechnology Department. And today I'm gonna be talking about looping oxygen to capture carbon, or in other words, how to move oxygen around to make CO2 capture cost effective. And unfortunately, I'm not gonna be talking much about direct air capture today. So that's disappointing for Hugh. Didn't work. All right, so this curve does not require a lot of introduction. It just shows CO2 emissions, but from the UK. And the most recent scenario created by the Committee on Climate Change on how to draw these emissions to zero by 2050. So what we will need to do is, of course, to reduce demand, improve efficiency, introduce deep electrification, but also produce hydrogen, implement CCS in industry and in energy, also implement greenhouse gas removal technologies to offset emissions. And interestingly, these four last categories involve in one form or another CO2 removal. And the CCC, so these guys predict that by 2050, we will need to capture about up to 175 megatons of CO2 yearly. So how to capture that CO2? This is a power plant, but this is just an example. The same idea or the same rules apply to any other process that use carbonaceous fuels, because if we have carbonaceous fuels, that we use them by reacting them with oxygen from air, that produces CO2. And unfortunately, CO2 is never alone because it's always in a mixture with nitrogen that comes from air. So at the moment, what we do with this mixture is we just emit it. But in the future, if we want to capture it, then unfortunately, that's not going to be easy because we're firstly going to need to separate the CO2 from nitrogen. And the state-of-the-art technology for separation puts this mixture through an absorber, which is a reactor, where we have amines capturing CO2, and saturated amines are directed to another reactor, a stripper, when they are regenerated, but regeneration requires introducing heat. And because we need to provide that heat, it means that we need to do work, so it induces some work penalty on our process. And the scale of that work penalty will depend on the level of dilution of CO2 in our mixture. And what this graph shows you is how inefficient separation unfortunately is, with the cost of separation changing logarithmically with the level of dilution. And the take-home message from this graph is that it makes much more sense, or it will save us a lot of money if we focus on capturing CO2 from concentrated streams. So indeed, this is usually how we discuss carbon capture. And here you have the work, that is theoretical work that we need to spend for separation of CO2 from nitrogen. And as expected, if we want to separate 400 ppm of CO2 just from air, we need to spend a lot of more work than if we separate CO2 from concentrated stream. And this is just a theoretical amount of work from thermodynamic calculation. In reality, you should expect numbers at least four times higher. But the natural question will be, can we make these streams even more concentrated? And the answer is yes. If we run reactions with pure oxygen or a mixture, artificial mixture of oxygen and CO2. And this way we will be able to produce a concentrated stream of CO2, and that will save us the work of separating it from nitrogen. So theoretically, case closed, but in reality, we still need to have this pure oxygen, and oxygen is produced also by separation because we need to separate it from nitrogen. And the amount of work that we need to put into this separation is similar to the work that we need to have for separation of CO2. But we can look for alternatives. And one alternative could be to use oxygen from a solid material, for example, metal oxide, that will give us the same benefit as running reactions with pure oxygen, namely we will produce concentrated stream of gaseous CO2. And this approach is called chemical looping, and it just allows us to skip the penalty for separation of either CO2 or oxygen. But what's the deal here in more detail? So we have a carbonaceous fuel that reacts with oxygen from a solid material. We produce concentrated stream of CO2, and then we leave behind this reduced solid material. And when we're done with this reaction, what we can do with this reduced material, we can just regenerate it, for example, with air or any other type of oxidizer, and it comes back to its original form of the metal oxide. So we're closing this type of chemical loop. And an overall summary reaction will tell us that what we've done is just a reaction with pure oxygen and producing concentrated stream of CO2. But we need to think a little bit with thermodynamics. So does it make sense to use chemical looping in this way? So here, what I show you is just the combustion of methane. It releases a lot of energy. We have large change in Gibbs free energy, and this is why we do combustion, because we want to produce work. But if we want to separate the CO2 and capture it, we need to spend part of that work either on separation of CO2 or production of oxygen. And if we want to switch to chemical looping, now we will have two reactions for two parts of the loop. And the first reaction, again, combusts methane, but uses a solid material. Here, an example is a copper oxide. And then in the second reaction, this material needs to be regenerated with air. But if you look at the energy products from both reactions, we end up with exactly the same result as we have from combusting methane directly, but we have produced a concentrated stream of CO2. So what happened, we had this separation, but it was completely for free. We didn't need to pay for it. So overall, the gains from this are clear. And physically, where they come from the fact that we have separated this process in chemical looping into two different reactions. And this separation is beneficial because it allows us to optimize reactions separately, also heat integrate them separately, and it gives us this gas separation basically for free. So from the thermodynamic point of view, this is an incredibly beneficial idea. So of course, it is not a new idea. It has been already used before. And in fact, for the first time commercially, it was used in 1906 by Briens brothers when they used barium oxide, a solid material, to produce gaseous oxygen. They later switched for the same process to cryogenic air separation, but the company still exists and you may know it as just BOC nowadays. Then chemical looping appeared again when Louis and Gilland wanted to patent it, nota bene a process that will produce pure carbon dioxide. And they wanted to use this pure carbon dioxide to carbonate drinks in food industry. Then finally, in 1987, chemical looping was proposed for energy production, then carbon capture, also for chemical processes. And nowadays, we mainly have experimental facilities with up to 1 megawatt of thermal power. So that's not really that much. So let's assume that you're now interested what this chemical looping is. You want to get into the business. You're probably going to ask a few questions like what type of materials can we use here, how to select them. So materials that can work for chemical looping will need to fulfill a few requirements. And the first requirement is, of course, they just need to give up oxygen when you want it. So how to judge whether material is going to give you oxygen when you want it? We need to look at phase diagrams. And here is an example of phase diagram for iron oxide, and it shows us when iron oxide is going to transition from one form of oxide to another. And with this example, we can see that we can actually have a range of transitions, even up to metallic iron. And another information that we get from this is that it will require quite a high temperature. Then the next obvious question is how much it will cost us. We want to have materials that are inexpensive. And fortunately for us, the market is already full of inexpensive natural ores. And in reality, we don't need anything more sophisticated than that. We can just use ores. Then we also want these materials to be robust, stable, safe, and so on. And with this range of requirements, we can now look for perfect candidate materials. And that was quite an interesting topic in the literature going on with a lot of studies looking even at theoretical materials that were never synthesized in the lab. Then what may also interest you is that how much oxygen actually is there that we can use from these materials. And of course, it will depend on the metal oxide that you're using. But if we look at the example of iron oxide being reduced to metallic iron, if we take 1 kilogram of iron oxide, which volumetrically is about 200 milliliters, so like a glass of iron oxide, it can give you with this reduction even up to 220 liters of oxygen. But if you're happy to just stop at this reduction, so at magnetite, you're going to get 10 times less oxygen, but this is still a substantial amount. And so with this large introduction, I can now give you some examples of chemical looping in practice, so how we investigate it in the lab. So in first example, this is for energy generation. We're going to have a natural ore-based material. This is pyrite. This is roasted pyrite that contains mainly iron oxide. So we put it in a fluidized bed in a reactor, and from the bottom we provide gases. And because this is chemical looping, we need to have two steps. First is this reduction, the second is the reoxidation, regeneration of the material. And in reduction, we use the mixture of carbon monoxide and carbon dioxide. In oxidation, we use mixture of oxygen and CO2, but we could have done it obviously also in air or other oxidizer. So what we see at the outlet of the reactor, here for concentration of CO2, CO is being consumed. So we see some consumption here, CO2 is being produced. If we had much more material inside, that what we will expect is that CO would be consumed completely and we would see only CO2. Then this part shows the regeneration. Nothing much happens here, but we know that the regeneration does take place because material is active in the next cycle and the next cycle and so on. And then we can also look at what is happening within the material itself. We can again look at phase diagrams. Knowing what kind of reduction mixture we have used, we can predict how deeply we will actually reduce this material. And then to get more insight, we can look or we can model how this reduction will progress by modeling sides of the starting iron oxide Fe2O3 hematite and how it changes to the product magnetite. And then we can model how the reaction progresses with time. So this is for reduction. And of course, that's going to be reversed for reoxidation. But just to sum it up, how it will be carried out, we will need to have two steps. In the first step, we provide some carbonaceous material and we produce concentrated stream of CO2 ready for capture. In the regeneration step, when we want to regenerate our material, we produce most of the energy. And this is what we wanted. So this is the first example. I'm going to show you another example because you may wonder, this example is for production of hydrogen. You may wonder why to do this regeneration in air, why not to use, for example, water. This is very clever because then we can strip water from oxygen to regenerate material and produce hydrogen. But we will need to be a little more clever about this because the presence of hydrogen within the bed will not allow us to regenerate our material completely. It's going to impose some thermodynamic constraints. So it's still feasible, but now we will need to look for a material that can loop between these two steps, even if the material is not completely regenerated. And a good candidate for this type of experiment is strontium ferrite, a perovskite that contains two metals. It's a good candidate because we know that it will reduce from perovskite to brown millerite, and then later we can even force it to reduce to metallic iron and strontium oxide. So we have tried this idea in the lab as well. And what you see here is the mass change from strontium ferrite during reduction and oxidation. And oxidation has been done here with CO2, which we use as a proxy for water because it's also a mild oxidizer. So if something works with CO2, it will also works with water. And we see from 30 cycles that generally the behavior is very, very stable. In the first cycle, we only saw like a larger drop in the first reduction. And this is because we started from the perovskite, so from the most oxidized, and then we forced it and we loop it only within this region. So we show that this is feasible to produce hydrogen by using chemical looping and still capture CO2. So this is just an example. I showed you two examples of how to use chemical looping. In literature, people have already shown that there could be many, many more reactions, and that's quite interesting. And Samuel is going to show you specifically two reactions that we are working on in the lab, and we have quite a lot of successes about. But what I want to reiterate that also this regeneration of material is very interesting because it allows us, for example, to produce hydrogen and bypass electrolysis completely. And the whole take-home message from me, if you want to remember something about chemical looping, it's a very versatile idea. It can be used for carbon capture, but also for heat generation, hydrogen production, production of chemicals, also air separation. And what we do in our lab, Energy Reaction and Carriers Group, we look at these processes at the interfaces. So how oxygen is being released, how oxygen is being captured when material is regenerated. And we want to manipulate these processes, for example, by adding catalysts and so on. We also look at the whole particle scale. So for example, by modeling what is happening with this particle when it reacts, but also what is happening with a particle of fuel, because we can have a solid fuel next to it. We also look at what is happening at the reactor scale or at the bundle of reactors scale. And we also can either model or we do experiments with these type of reactors and reactive multi-phase flows, also looking what is going to happen if we add biomass or similarly attractive fuels. And finally, we also look at how chemical looping can be implemented on a larger scale, on a system scale, and Samuel is going to give you some more results about it later. So as you see, there's quite a lot of going on here. This is quite an interesting and exciting idea with a lot of new things coming up. Our group is expanding. We are looking for PhD students, but I guess the audience already has decided mainly on their PhD careers. So at this point, I want to thank everyone who's involved in the research that I was showing to you today. And I want to thank you for your attention.
Thank you, Eva, for an interesting talk and for the introduction about chemical looping. Can I invite any questions to Eva to come up in the Q&A now, please? I think there are I think there are quite a few questions there in the Q&A that are still for Hugh, and Hugh has rejoined us now, but he's unable to see those questions. So I'll work out how to get those questions to him after this Q&A session. But here's one question for Eva from Sean Fitzgerald. So he's asking if looping can be used to help carbon capture and storage, should the current processes under development be changed to looping?
I would say yes, but I'm generally advertising chemical looping. We will for sure need to have some installations to see what are the problems with just running processes with solid materials. There are some installation, of course, already, but we need to scale it up. And I think this is a usual problem with most of the capture technologies other than capturing with amines, that we just need to spend time on learning more, and we probably need to accelerate this learning curve as fast as possible if we really want to capture that amount of CO2 in the scale that we're aiming for, so in the next 30 years.
Yeah, okay, great, thank you very much. Are there any further questions for Eva at this stage? I think all the ones in there are for Hugh. I'm sorry, trying to keep track of which questions are going where. Okay, so I think we'll then, if anyone has any further questions for Eva, please add them in the Q&A, and then if you want to type answers to those, Eva, that would be great. And then we will move on to our next speaker. Our next speaker for today is David Coomes from the Department of Plant Sciences. So David, I will hand over to you.
Thank you. Trying to get full screen here. Oh, there we go. Got full screen. Okay, so I'm going to talk today about planting trees to save the planet, greenwashing or golden opportunity. Planting trees is a part of a sort of set of ideas on the table for climate change mitigation called nature-based solutions. And these are meant to be solutions to societal challenges that involve working with nature. That's a very broad definition, but there's the climate crisis we want to resolve. And there's also a biodiversity crisis where many species are imperiled across the planet. And there's this intersection between those two crises, which could be solved, we hope, by nature-based solutions, which think explicitly about the climate crisis, biodiversity, but also how we can help human well-being. And I was just really intrigued by this report, which came out very recently. I don't know how many people have seen this, Task Force on Scaling Voluntary Carbon Markets. And the people involved are quite senior here. They've got Mark Carney running the show, and Bill Gates recommending we read this, looking at voluntary carbon markets, which is what's one mechanism for supporting these nature-based solutions around the world, and why they're not working very well at the moment, and how they could work better in the future. And so this is from this Carney's report, and what they're suggesting is that in order to get to keep within 1.5 degree centigrade temperature rises, we need to have to allow no more than 570 gigatons of CO2 to go into the atmosphere between now and 2050. And in order to achieve that, we've got to meet these targets. And one of these is that by 2030, we've got to be consuming, to be emitting 23 gigatons of CO2 less than we are today. That's an enormous amount of CO2 reduction by 2030. And the second thing which to point out from this graph is that by 2050, any residual greenhouse gas emissions have got to be offset by some sort of sequestration into a different system. So Carney and this report is arguing that some of this minus 23 can be achieved by what's called nature-based solutions. And here's their next graph from this report. And so it's saying, so the key, can you see my mouse? I'm not too sure if you can, but anyway, it says practical potential. Can you see my mouse? It's sort of moving in random ways at the moment. I'll try and make it more targeted. So this thing, practical potential here, is what they think is conceivable and possible perhaps by 2030. 8 to 12 gigatons of that 23 I just mentioned could come from these what's called carbon credits, paying for carbon to be removed from the system. And these first two, so 3.8 and 2.9, are from nature-based solutions. We've got avoided nature loss and we've got nature-based sequestration. So I'm going to talk a bit about these two in a moment. But the key thing is this green one on the end. This is what they actually think is likely to be achieved at the moment, unless they overcome lots of obstacles, including financial structures for paying for protecting natural systems. So as a biologist and ecologist, what I'd really love to see saved, and would make an enormous amount of sense for reducing emissions, is tropical forests. They're disappearing at an enormous rate, and each hectare of forest might contain 300 tons of carbon. So stopping this from going into the atmosphere and paying for that seems a really good way forward. And the mechanism for doing that is called reducing emissions from tropical degradation and deforestation. And essentially what we've got is over here carbon stocks, say it's a country, and over time, because of deforestation, the carbon stocks are going down. And if we kind of extrapolate that line through, beyond the start of a RED project, then this is what the line would look like. But actually the RED project is effective in reducing that deforestation rates, avoided deforestation. So we've got two lines here, the extrapolated line and what actually happens. And the difference between the two is emissions reductions, which could be paid for through some carbon financing mechanisms as a carbon credit. And so this sort of scheme has been trialed for about 10 years now. It's still, they're still tiny on the global scale of what's needed. And there's been many issues with them which haven't fully been resolved, not least indigenous rights. But there is promise of this sort of mechanism into the future as really helping with the carbon mitigation, but also saving biodiverse tropical forests. And then another set of solutions involve planting trees. And here we have some conifers up in Scotland, but they could be eucalyptus throughout the tropics, planting trees on what might be described as wasteland or agricultural land or whatever. And these trees are soaking up carbon in their tree trunks. And so that must be a good thing. And so this sort of thing is something the Conservative government and Zach Goldsmith are really contemplating at the moment. What should they be doing as in the run up to the COP26? To what emphasis should they put on the developing world and helping find solutions there versus doing things in the UK itself? And Zach Goldsmith, actually Boris Johnson himself, has declared he wants to have 300 square kilometres of new woodland in the UK every year from 2025. So that's an enormous amount of woodland Boris, in the run up to the election, promised he'd plant, well, not personally. And the question is, where would that go? Is it going to work as a climate mitigation solution? So first thing to point out is and I'm going to talk about the UK primarily for the rest of my time. So the UK is one of the least forested countries in Europe. it used to have a lot more woodland than that, but we cleared it for agricultural land a long time ago. So there in itself is some rationale for getting more woodland back. And woodlands are valuable in different ways for different services. So they're potentially valuable for offsetting carbon emissions, as I've just mentioned. Human well-being, we've got nice bluebell wood and nature and people loving that. And then we've got wood production, and that could include wood being used for power stations like Drax we've got here, and there's other services as well provided by woodlands, including flood relief. And so this very influential report from 2009 made the case for expanding woodland cover in the UK, primarily to mitigate and adapt to climate change. Sorry, I've got a few very wordy slides here. So the UK currently stores 4 billion tons of CO2 in the woodlands, and they soak up 4.6% of the country's total emissions. So not a huge amount on the grand scale of things, but they are a net carbon sink. The interesting thing is that the natural capital, this is the UK's statistics office, the natural capital, the value of the non-market benefits of the woodlands are about 12 times the market values of the wood production. So we think of woodlands being valuable for timber, but actually if you look at the value of carbon, that actually they're much more valuable for the carbon they store, according to the government's own offices. And so planting 300 extra kilometres, if we can find somewhere to put them from 2025, offers opportunities to mitigate climate change by soaking up carbon dioxide. This is based on a public talk to the public, which has got some very soaking up words here, not very scientific, although the full benefits will not be felt by 2050. And so the Reid report actually did some simulation models. They're a bit out of date now, but they said what would happen if we put in, let's say 300 square kilometers of forest a year. And the red line is what would happen to the carbon sink. And we can see that if we planted those forests, and they're very fast growing, then actually they'd gradually increase the carbon sink across the UK. And by 2070, we would have a fairly substantial carbon sink in the forests if we planted that amazing amount of forests across our country. And so here would be the idea that we'll be working hard to get our fossil fuel emissions down. And actually, at the same time, this wood carbon sink is increasing and starting to play a much more significant role in offsetting the carbon emissions we can't get rid of. So there's some really hard choices to make if we're going to do this, and the government seems fairly intent on it. One of them is what are the biodiversity values of different approaches to planting woodlands. And I'm a strong advocate for planting native species close to our sites of really special sites for nature already. Are what's called ancient woodlands. We've got 42,000 tiny patches of ancient woodland left in the UK, and we can plant new woodlands around those, buffer them, and reconnect them. That would be fantastic for nature. So that's one argument. Not actually the best one for carbon sequestration, which comes us onto the next slide, where to plant these trees. Now, we've got some choices here. We could plant them on what's called grade 1, 2, or 3A agricultural land. That's the very best land for growing crops. Now, if we were going to do that, the trees would grow flipping fast as well, because it's really nice land, but we'd be taking land out of crop production, and it's very expensive land as well. And if we take crop land out of production, we're going to have to bring the food in from somewhere else in the world, which might well mean removing tropical forests. So there's a problem there. We might solve the problem of climate change mitigation. We might be mitigating some climate change here, but actually we're making the problem worse by importing forests coming from food coming from tropical forest clearance. Similarly, if we go on to poor grazing land, class 3B, 4 and 5, there's lots of that, then that could work, but we actually need to reduce our meat consumption across the UK for that really to work. Otherwise, we do the same thing. We take the problem elsewhere. We're getting Brazilian beef from deforestation of the Amazon, for example. So unless we actually couple this woodland expansion with reductions in our consumption of meat and dairy products, or massively increase our production on the lands which we intensively use, that's not going to be a great solution, but that is probably the best solution of the three if we're going to expand. Peatlands are effective at carbon offsetting, but the land is very cheap. The problem with peatlands for planting trees is that you have to drain them, and in the process of draining them, they emit a lot of CO2, so that they create what's called a carbon debt when you drain the peatland. Lots of emissions, and that can take many years of tree growth to offset that initial loss of CO2 from the system. So actually peatlands, deep peatlands, are already banned for planting forests. Shallow peatlands, there's a great debate going on at the moment. Of those three, probably planting trees on mineral soils, on poor grazing land, which has got low diversity, is the best of the three solutions, but we have to eat less meat if it's going to have a big effect on the planet's climate balance. Trade-offs, which species? Native species versus non-conifers. Well, I put my preference down. It depends ultimately on what we want to do with our land. If we want to produce more timber, and there's an argument for that because we import a lot of timber, then we do need to plant more conifers across our landscapes. But we've got to be careful where we put those conifers and not create these carbon debts by disturbing the natural peatlands. A second thought is burning wood. I'm going to pick a bit up on Hugh's point from his first slide. I think using wood as a biofuel is a really bad idea. And what Drax is, I think, completely reliant on that, or maybe 3/4 reliant on a biomass for its energy sources, but that's not coming from the UK. If we used the wood from the UK, that we would be using all our wood production and slightly more, I think, in order just to fuel the Drax power station. And that's because plants are really inefficient, actually, at converting solar energy into usable energy. They're about 100 times less efficient than a solar panel. And so we'd need a huge amount of land to do that. And at the moment, we're importing wood from North America, or at least last time I looked at this 3 years ago. And because of accounting rules, we're not really tracking what's happening with the forests in the US when we're doing these transactions. So we're not keeping track on whether those forest carbon stocks are being reduced in order to supply us with wood. And it seems very likely that they are being reduced. So the carbon benefits of this approach is less than clear as well. BECCS, a possibility for the future, but not achieved at scale anywhere at the moment. So until we have further information about whether it will work, I think that's a challenge. So to close, greenwashing or carbon or golden opportunity, planting trees, that should be. A, our priority must be decarbonisation. I think that's really clear. And many organisations have signed up to a sort of nature-based solutions set of principles now where they've made that the sort of top priority, that we mustn't think of this as a way of not doing the decarbonisation bit. That's every company must think about decarbonisation first and foremost. Protecting natural forests and peatlands could be a win-win-win for climate mitigation, biodiversity and people, but it has proved challenging to implement so far, and I think we just need to work on improving the way we're doing things. Using wood as a biofuel, I think, is really problematic because it's very inefficient at converting solar energy to usable energy. Planting trees can be good, particularly increasing domestic wood production, but I think we just need to be very careful where they go and think about them on a site-by-site basis. So there we go, that's my talk, thank you.
Thank you very much, David, and thanks for also the interesting discussion there around bioenergy, and it's definitely a topic of debate, clearly. So there's a few questions for you here in the Q&A. So the one from Matthew Burnett asking, is there a large enough carbon offset market to support global scale biodiversity protection? And who owns the protected land at the end of the scheme?
So repeat that one. So what's the first bit? Is there a big enough carbon market?
To support global scale biodiversity protection, yeah.
So if you're interested in that, have a look at the Carney report I just mentioned. The market is growing enormously at the moment, and and part of that is, you know, big business investing in it because they see these carbon credits as a, you know, a way to bring down to achieve net zero within their organizations. So the market is expanding rapidly over the last few years after a sort of languishing with very little capital value for the last 10 years.
Right, thank you very much. Another question here from Len Dimmock saying, growing trees for removing CO2 may not be reliable. Verifiability is central to making net zero accounting sums add up. I guess that's more of a statement kind of adding up with what you just said.
No, and it's very, very true. Yeah. But I mean, I think that's a solvable problem.
Yeah. Okay. Right. Sean Fitzgerald is asking, how do the benefits of planting trees compare with alternative strategies such as changes in agricultural practices to increase carbon content in the soil, or using some land for growing fast-growing trees and then using this as a source of biochar to spread on fields?
My mistake, Sean, I admitted to mention soil, agricultural soils, in that was the second category in that Mark Carney diagram at the start there, would include agricultural land increasing carbon. I don't know the answer to your biochar question. I think there is, because there's so much agricultural land, changing the way we manage that land to store a bit more carbon in the soil can be enormously influential. But I think the Carney report doesn't have that as the largest quick gain, potential gain in its bar charts there. So I'm referring to that one.
Okay, thank you. There's lots of questions coming in, so we're not going to be able to get through them all live, but I'll do a couple more. Are there proposals, this is Madeline Han asking, are there proposals for a government entity which would be charged with deciding which trees to plant and where? Theoretically, a centralized body could help reduce incidence of monocultures, non-native planting, and use of peatland for tree planting.
Yes, there is. There's something called the UK Forest Standard, which any planting has to follow this set of rules, this guidelines, and so there's a lot of discussion about at the moment about whether those set of rules are strict enough and right enough. Planting on peat is a classic example where new planting on deep peat is banned, but planting on shallow peat is still allowed. But there's lots of questions at the moment about whether that's the right thing. And I think pragmatically it will be a balance at the end of the day in the UK between more plantations and what I'd love to see more native forests for biodiversity and people. And then inevitably, if there's this huge expansion, it's going to be some mixture of those three, and and that's still to be worked out.
Okay, thank you. Alex Archibald is asking, how important is future fire risk when it comes to nature-based solutions? We've seen increases in wildfires in the UK recently.
Wow, if Adam Pellegrini was on the line, he'd love that question. We've got a new lecturer who's a fire expert. Some evidence for new peatland fires actually release a lot of CO2 up into the atmosphere, as I'm sure you know. And the sort of permanence of nature-based solutions is a constant issue which people are grappling with, and obviously some parts of the world the permanency is much more questionable than other ones. And actually the Carney report I see sort of filters out large parts of the earth when it's making its calculations with this permanence question in mind.
Okay, thank you, David, for answering all these questions. I think I'm going to have to ask you to carry on to type answers to the remaining questions now. There's another 5 there I can see, and more keep coming up. It's clearly lots of interest in this topic. Is that all right for you to type answers to those?
Where are they? Just in the Q&A? I'm looking at the wrong thing. Okay.
Go in the Q&A box, yeah, and then type. There's a type answer function.
No, that's good. I'm there. Thank you.
Great, thank you very much. And I think we've also managed to answer all the questions that were put to Hugh earlier on. We've also managed to get his answers in there. So I hope that everyone's questions are being answered. We're going to move on now to our next speaker in the interest of time. So our next speaker is Dr. Zeynep Clulow from the Energy Policy Research Group in the Judge Business School. So Zeynep, over to you, and I'd like to invite you to share your screen, please.
Yeah, I'm just trying to bring that up.
That's right. And Zeynep will be speaking on socio-economic and political challenges to negative emissions technologies. So continuing on nicely on the theme here.
Hopefully you can see that in full screen.
Yes, we can, yeah.
Okay, thanks, Eric. I'll really be talking from a social science perspective. The rationale for, or at least the political will for negative emissions technologies is often linked back to the Paris Agreement and to the commitment to try and keep global warming below 2 degrees Celsius and subsequent commitments to try and limit it further to below 1.5 degrees. There's a strong consensus among analysts that our ability to meet an ambitious temperature target really depends increasingly on nets. And this graph doesn't really require much explanation, but the blue shaded region shows the pathways or the scales of nets deployment, which are really compliant with Paris. And you can see by the middle of the century, there's a need for kind of considerable deployment of nets in order to meet an ambitious temperature target. Despite the strong scientific consensus and the kind of growing political will surrounding nets, that there's a significant gap between where we are at the moment and kind of recommended scales of deployment. So I think it's helpful for a moment to consider current practices in light of these recommendations. Until recently, the focus of most assessment models have been two nets in particular, so afforestation and reforestation, and also bioenergy and carbon capture and storage. And it's often recommended that AR is deployed at a scale enough to remove 5 gigatons of CO2 from the atmosphere per year, and BECCS at 12 gigatons. And where we are at the moment is closer to 1 gigaton, and actually most of that is due to carbon which is stored in the tropical rainforest rather than any major nets projects. So there's a significant way to go in terms of upscaling if we are to meet the Paris targets. Efforts to explain the slow rollout have tended to focus more on technological and design issues, and I think to some extent there's good reason for this, because most of the nets are rather new technologies, and there are important design issues which need to be addressed. As an example, enhanced weathering and ocean fertilization, they're associated with a number of unknown risks, and there's really a need for further scientific research to evaluate whether it's kind of worth pursuing these options further, and which kinds of challenges are going to emerge. But increasingly, policymakers and scholars are emphasizing the obstacles posed by kind of socio-economic and political factors. So nets projects aren't being deployed often because of these reasons. And this is perhaps clearest in relation to the more familiar nets, so AR and soil carbon sequestration, which have been a practice for decades, if not centuries. So the major hurdles here aren't really technological, but they're more practical problems. So as the previous presentation suggested, it's particularly difficult to count carbon flows in the soils, and previous forestation projects, for example, have often had significant negative effects on host communities. So countries that have hosted these kinds of projects in the past, say under the clean development mechanism, are often reluctant to host them again. There are also important trade-offs between the different nest options and other political priorities. So as an example, AR and BECCS require lots of water and land, and there are real fears that large-scale deployment would detract from resources from agriculture and result in rising food prices. Another example is enhanced weathering and direct air capture. They're very energy intensive, so large-scale deployment could pose problems for energy security. And then at the lower part of the figure, you can see there's a kind of potential conflicts between the different technologies and the sustainable development goals, and there are quite significant divergences between the technologies. Governments, to a large part, have been interested but cautious, and I think certainly interest has grown, and in parallel with the rising number of countries to adopt carbon neutrality and net zero targets. But there are also good reasons for governments to be cautious, and I suppose the one that I'll be focusing on in this presentation is the kind of a difficult balancing act that policymakers really need to do in terms of reconciling the divergent views and interests of various stakeholders, as well as the potential conflicts between large-scale nets deployment and other political priorities. The private sector is also interested, and I think increasingly interested in parallel with the adoption of more ambitious temperature targets. I think with the net zero targets in particular, there is a growing expectation that corporations need to play a role in helping to meet temperature targets. And as a result, private sector interests are becoming more interested in nets as a means for reducing their own carbon footprints and also for offsetting emissions from within their sectors if they're unable to do this in the short term. So three sectors which are particularly important and high carbon, so have potential to play a big role in upscaling nets are agriculture, energy and transport. And agriculture is important because most nets involve land in some way, so either for growing biomass or for storing carbon. So it's particularly important that governments are able to offer appealing incentives to work with the agricultural sector if they're going to be involved in facilitating deployment. Energy and utilities and transport and aviation have tended to focus more on carbon capture and storage based options, so either direct air capture or BECCS as a way for reducing emissions within their own sector. And then there's also growing interest, especially from aviation, in investing in forestation projects in parts of the world which are best suited to these kinds of activities as a way to counterbalance the emissions from within their own sector. NGOs, I think, have been the most opposed to nets, although there are important divergences between the different organisations and also towards different technologies and even when talking about the same technology, about different scales of deployment. So there is a tendency to kind of perceive or characterise rather nets as a dangerous distraction from mitigation because of the option of offsetting emissions today with negative emissions in the future. NGOs have tended to focus on the risks associated with nets. So these are kind of physical risks, but also broader social and equitability related risks associated with the major land use changes. And I think it's possible to suggest that NGOs have become slightly more positive in their outlook, at least some of them have, as governments are starting to take nets maybe more seriously and demonstrate a growing commitment to them. So WWF, for example, has outlined some practical steps and principles that should be followed if nets are to be deployed in a sustainable way. Publics are generally not very well in tune with nets, so awareness is low, and for the minority who have heard about nets, opinions tend to be negative. But there are a couple of key distinctions I think worth mentioning. So the first one is between these nature-based, so forestation and soil carbon sequestration types of activities, which are seen as more natural and acceptable, in contrast to the newer technologies, which are often seen as futuristic and negative. And then there are also distinctions to be made between publics in developed countries, which tend to fund, which have at least historically tended to fund forestation projects, and developing countries which have tended to host them. And obviously the latter have had first-hand experience of some of the negative side effects of these projects, so they tend to be more opposed. So by way of conclusion, I just wanted to kind of reflect on the potential role for governance to help address at least some of these challenges. And I think on the face of it, governance of nets appears to be a very technical exercise. So there's a need for strong regulations to govern incentives, markets, accounting, and to monitor the risks that are associated with these technologies. But if we take a closer look at any of these aspects, I think we'll find that each one of them raises highly social and cultural and sometimes even ethical issues which need to be addressed. So if governance takes a kind of broader approach and engages with these social issues, I think that it could play an important role in helping to alleviate some of these problems. And just as an example, kind of a key and obvious way to do this might be to allow enough opportunities for stakeholders to express their opinions and raise their concerns early on in the decision-making process. And it's also a pragmatic way for making sure that project developers are kind of incentivized to engage with these issues and preempt serious opposition from arising later on in the deployment phase and resulting in aborted projects. And that's the end of my presentation. Thank you.
Thank you very much, Zeynep. It's great to get the social and governance angle on this as well, and consider that aspect. So I'd like to invite any questions from the audience for Zeynep. I think all the questions in the Q&A are still ones from David Coomes' presentation. I was just going to ask you, well, while we wait for any more questions to come in. Oh, hang on, here's a question just come in, right, from P. Suschelin. Is there a risk that scientists communicate about nets in a combative way, reducing public perception? I'm not quite sure what I mean reducing, but.
Well, I think framing has definitely been found to be important. So the way that that technologies are in a way kind of, or the different aspects of the technologies which are emphasized. So focusing more on risks, for example, might raise more questions and result in more kind of opposition or concerns, at least. So the way that nets is communicated is definitely important. I'm not sure if I addressed the aspect about combating that. I didn't quite understand that.
I think that's yeah. I think you did address it. I think the question about whether the nets are presented in a more combative way rather than a. So yes. I was going to ask whether you think that the UK government is doing enough to address the challenges you outlined about governance and public perception.
I think the UK government is definitely kind of leading in terms of developing a coherent strategy towards nets, and there is a diverse and rich kind of research on public perceptions in the scholarship, at least. I'm not sure about, there are kind of efforts to develop public information campaigns, but these are still very early stages, so perhaps a bit soon to say.
Okay, thank you very much. I think we'll move on to our next speaker then. But if there are any more questions for Zeynep, then please put those in the Q&A, and you can type an answer in the Q&A. So our next speaker today is Dr. Paul Griffiths from the Department of Chemistry, and you're already sharing your screen there. Great. So over to you, Paul.
Hi, yeah, thank you very much. Just need to figure out my spotlight. Hopefully you can see that as well. Yeah, yeah, thanks for the invitation. I'm Paul Griffiths, an NCAS research scientist working in the chemistry department. And our interests are in the atmospheric chemistry of radiatively important gases such as methane and ozone, and in the role of feedbacks, such as those mediated by aerosols in the climate system. And the work I'm presenting here has been done by a team of us in atmospheric sciences. And if you're quick and you scan the QR code, you can find a link to the slides. My talk examines the atmospheric impact of a partial shift from fossil fuels to hydrogen as a fuel source. And the motivation for this shift is that hydrogen, when combusted, ultimately generates water vapor rather than CO2. Now, how the hydrogen is generated in the first place is outside the scope of our work, although it's clearly a big part of the story. So I'm going to focus here on the impacts of hydrogen releases in some idealized scenarios that are intended to inform policy discussions, and I'll focus mainly on radiative forcing changes. Which means I need to introduce the concept of radiative forcing. For a system at equilibrium, we would expect the incoming solar radiation to be balanced by the outgoing thermal radiation. And the equation at the bottom here highlights the connection between the change in global mean surface temperature, delta T, with a change in this radiative flux, delta F. Small changes in the flux are going to be proportional to the temperature, and the constant of proportionality, lambda, which is positive, is estimated from separate experiments, for instance, doubling CO2 in climate models. Sadly, calculation of delta F and delta T are not straightforward. And in case you were wondering, the parameter lambda is also up for debate. But working within this framework gives us at least a connection to the IPCC assessments of climate change and gives us some confidence that the numbers that we calculate are comparable. We do know that from this picture and from other ways that the story is not just CO2. And it raises the question, how does an atmospheric gas like carbon monoxide, which is not a greenhouse gas, give rise to a positive radiative forcing and hence a positive temperature change? And the upshot is that these gases react in the atmosphere via chemistry which resembles low temperature combustion, and it involves free radicals. And these reactive free radicals also control methane, which is a potent greenhouse gas, the formation of ozone, and secondary aerosols, which are highlighted here and which cool the climate. The oxidation of CO2 therefore results in CO2, of CO rather, results in CO2, but also has effects on methane and ozone, which are themselves greenhouse gases. The interesting thing is the role of aerosols and the reaction in the atmosphere between free radical oxidants and anthropogenic emissions like SO2 lead to the formation of aerosol particles. Oops, wrong way. Leads to the formation of aerosol particles. And these so-called secondary aerosols are important in the climate system because they provide the germ for cloud formation. And changes to the number or characteristics of these aerosols can affect the resulting cloud properties. And this provides a route for the changes in oxidants to affect cloud properties, and this will need to be considered in our assessment of radiative forcing. The coupling between the various species in the system means that we are probably best advised to use a model to figure out the interactions and the impact. And this is where an atmospheric model with good aerosol microphysics can add value. So to come back to my topic, which is hydrogen, it has a variety of sources and sinks. I've summarized them here. There are some contentious numbers among these data, and the uncertainties, as you can see, are rather large. As in the case of carbon monoxide, it combusts in the atmosphere, albeit with much less vigor than a normal combustion reaction, and so there are no squeaky pops as the hydrogen is combusted. But as in the case of carbon monoxide, the free radical chemistry and the oxidation lead to the formation of ozone, and I'm summarizing here some of the impacts. The atmospheric concentration of hydrogen at the moment is about 550 parts per billion by volume, and it has a lifetime after emission of about 2.5 years. So my colleague Nicola Warwick devised some scenarios where we considered what fraction of the global energy production was susceptible to replacement by hydrogen power, and then asking what fraction of the required hydrogen would escape into the atmosphere. And we found that these scenarios were pretty well bounded by a range of hydrogen concentrations or resulting hydrogen concentrations up to 2,000 parts per billion by volume, or about 2 ppm. So that's like effectively a quadrupling of current day levels. I won't talk about them here, but we've got a bunch of experiments done where we look at the co-benefits of a move to a hydrogen economy. So if you move to hydrogen economy, what happens to things like carbon monoxide and nitrogen oxides? And if anybody's interested, I'd be glad to talk to you about these. We performed our experiments just by, our experiments in which we modify the hydrogen concentration in the atmosphere using the Met Office climate model, which has a detailed chemistry, radiation and aerosol schemes in it. And we performed our experiments simulating changes in hydrogen for the year 2014, so present day conditions. And we found that the effect of increasing hydrogen in the atmosphere is to provide a small warming. What we found is that the radiative forcing increases with hydrogen concentration, and it reaches a plateau at the highest levels of about 0.15 watts per meter squared, which is about 5% of the warming effect of CO2. The as I say, this is despite hydrogen itself not being a greenhouse gas, but it just couples into the atmospheric chemical system in a way which changes the radiative forcing. 2000 ppb of hydrogen actually corresponds to an incredibly optimistic picture of how hydrogen will be taken up as a fuel across the globe, but it has a very pessimistic view of our abilities to constrain hydrogen leaks. And it's based on a leakage rate of 10%, which is at the high end of current ranges. So we've got, maybe you would say, the best case scenario for uptake, but the worst case scenario for our ability to constrain fugitive emissions. We held the methane levels deliberately constant so that we have a better access to attribution of what drives this radiative forcing. And we can see that in the highest hydrogen experiment, we have an increase in ozone of about 5 teragrams or so, which we believe would lead to an increased greenhouse gas effect. And we can actually drill down further into these radiative forcings by taking a global picture of the energy balance at the top of the atmosphere. And we can break the radiative forcing down into sort of clear sky effects, which target the greenhouse gas effects of emissions, and then the effect on clouds that I alluded to before. In the case of the clear sky forcing, which is to say the greenhouse gas effect, we find a positive forcing, so that would drive a temperature change at the surface, which would also be positive. And the clear sky forcing is about 100 milliwatts, so maybe 2/3 of the overall effect. And this is presumably because we are, by emitting more hydrogen, we're producing more tropospheric ozone, which is a greenhouse gas. There's also a change in the cloud properties. This is also slightly positive, and the largest effect there is in the shortwave, in the visible region where cloud albedo has an effect. And so the hydrogen emissions are also changing the cloud albedo slightly. And my final slide, there we infer that the decrease in these free radicals OH is giving us a lower cloud droplet concentration in our experiment. So as hydrogen increases, we see progressively fewer cloud droplets. And this fewer droplets leads to a change in the albedo. It actually makes the clouds less reflective, so we're reflecting less radiation out into space, and that shows up as a positive forcing in our calculations. So my conclusions are that the hydrogen emissions, the shift to a hydrogen economy, couples into the radiative budget of the Earth via its effects on atmospheric oxidants. One of the effects is that the hydrogen through this low temperature combustion leads to slightly enhanced levels of tropospheric ozone, which is a greenhouse gas. Hydrogen also functions as a sink for OH, which is an important atmospheric oxidant. And this change in the oxidant level, this decrease in the oxidant level, actually leads to fewer CCN in the atmosphere, which produces a decreased albedo, which shows up as a positive forcing. So far from my talk, I think you'd take home the fact that controlling these fugitive emissions of hydrogen is important. Results that I haven't shown indicate that the coupling between hydrogen and methane can be particularly strong, and that we also find that if the hydrogen is adopted but the leaks are controlled, we see a significant benefit for radiative forcing. We can actually decrease the radiative forcing due to methane and ozone by just constraining the leaks. So it's not all bad news. With reductions in methane, we could actually achieve a reduction in forcing of 0.3 watts per meter squared, which is about 30% of the overall radiative forcing due to methane. And with that, I'd like to thank you for your attention.
Thank you very much, Paul. That was really interesting. I would like to invite any questions for Paul now in the Q&A, if anyone would like to ask anything. I was just going to ask myself, you mentioned you use different scenarios of how much hydrogen would be used in future for different fuel sources. I guess, I mean, from my understanding, there is a huge debate over what will and will not be powered by hydrogen in future. So there must be a large range of different scenarios there. How did you choose those scenarios and what are they based on?
Yeah, we did a lot of thinking about the about the sectors that were susceptible to modification by using hydrogen as a fuel. Nicola is the expert, but my message from that was that it's heating that's the main thing that can be switched over with relatively little penalty, and so heating of domestic and business venues was quite a big potential benefit there, and of course that shift also leads to reductions in things like NOx emissions. So it was quite interesting to see how the sectors were susceptible to modification.
Okay, and I think Hugh's raised his hand there as well. Hugh, did you have a question or not? No, okay, sorry, I got that wrong. One question just coming here for you in the chat. Did you also consider the reduced methane emissions from gas grid leakage, etc., and how that would decrease the forcing compared to the increase from hydrogen?
No, we didn't, but I'd love to do that. I think those kind of systems approaches are really powerful and add a lot of value. So, Richard, if you ever want to shoot me an email about scenario construction, I'd be glad to get it.
Great. Okay, that sounds like a good collaboration right there. Okay, we'll move on now to our next speaker for today. This is Dr. Ellen Quigley from the Centre for Study of Existential Risk. And Ellen's going to tell us about how to decarbonize the financial system. So over to you, Ellen.
Yes, a bit of a switching of gears here today. It's been absolutely fascinating to hear all of your presentations. I'm going to be talking about the money, the flow out of climate change causing activities and projects and into the good stuff. And I'll only have one slide because I'm going to try to really make a point about debt. So just to flag that ahead of time. So we've already heard a bit about Mark Carney's task force on nature-based solutions, and I want to talk about a different task force of his, the Task Force for Climate-Related Financial Disclosures, TCFD, and why that sort of thing is not what is going to allow us to decarbonize our financial system, which is obviously critical because that's what finances all of these resources that we need to decarbonize. And also, conversely, are currently financing things that are contributing to the problem. So TCFD and I'm just going to take a shot at responsible investment, which is my field as well as environmental, social, and governance investing, ESG. So I'll be referring to anything in the realm of responsible investment as just responsible investment, but it includes all of these other acronyms. The idea is to look at what the purpose of responsible investment typically is and whether or not it's fit for purpose to actually decarbonize the economy. And unfortunately, responsible investment now is typically centered around stock picking in public equity. And by public equity, I mean companies that are listed on the stock market. And what's important about that is that the stock market is a secondary market. So that's not where new money is flowing into companies. It's where we trade existing shares of companies. So just to illustrate this for a moment, if you sell a share, by definition, another shareholder is buying it. It doesn't actually affect the company. You'd have to have a lot of sales, an inconceivable number of sales of shares to actually affect the share price. And even that very well might not trickle down into any effect on the company or its decisions. So that's where the focus tends to be. And let me just take a side note for the moment to explain that this is a different concept from divestment. Although divestment is aimed at selling shares and other financial instruments in fossil fuel companies, the goal is very different. So the theory of change is that you have to demonize a sector so that it can become viewed by the population as a sector that needs to be legislated or regulated, because we don't tend to legislate things that we don't view as problematic as society. So most divestment activists, if you talk to them, they're not trying to affect the cost of capital or whatever. They're not trying to have a direct effect on companies. They have a broader theory of change. So just to put that out there. I'm not insulting the university's decision to divest from fossil fuels. But other decisions to sell shares in various companies for various reasons, it's rearranging deck chairs on the Titanic, to be frank. because that's not where new external financing is coming from. And this is where I'll share my dramatic slide to illustrate the point. So can you see this?
Yep, we can.
Great. So what you see here is the proportion of total external financing for fossil fuel companies that comes from debt. So that's all of the red and the blue. About 90% of new external financing for fossil fuels comes from bank loans and bond issuance. And bonds are just when a company wants to have investors lend money to it. They sell bonds and investors buy them. And critically here, banks also underwrite these bonds as well. So about 90% of financing can be traced back to the debt markets. And the orange bit at the bottom, it's worth pointing out, that still isn't to do with selling shares on the secondary market. That's private equity, venture capital, and what we call an initial public offering. So that's the moment that a company lists on the stock market in the first place. That's when they actually do get money from shareholders. And occasionally, very occasionally these days, you'll see a new issuance of equity on the public market, but that's very much a rarity. So if you think of the extent to which new financing is coming from asset classes other than public equity, you can see why the efforts around responsible investment are not aimed at actually having an impact on climate change. Their goal, rather, is to avert risk to the company or to the portfolio of the investor. And this is where we come back to the TCFD, the task force that Mark Carney ran prior to the newest nature-based one. That is aimed at disclosing the risks that a company faces from climate change. So let's say rising sea levels might contribute to the loss of real estate along coastlines, that sort of thing. And in a very extreme sense, I'm not saying this is exactly how it plays out, but let's say you take a company like Exxon. If you're worried about the impact that climate change has on a company like Exxon, you would want them to raise the levels of their oil rigs in the ocean to account for sea level rise coming from climate change. You would not concern yourself so much with their contribution to emissions through their activities through selling oil and gas. So it's very much a flipping around of the narrative around responsible investment to look at the actual impact that your investments have on the real world. And it means that you look very differently across your different asset classes. So that means that when you're looking at bonds and you're looking at private equity and venture capital and so on and so forth, then it really does matter what you buy or what you own. But with public equity, unless you're making a big divestment announcement and contributing to that public discourse change, it makes a lot more sense to engage. But most engagement to date has been less effective than we might wish. And having reviewed the evidence on this, there are a few things we could do a lot better. There's actually quite a lot of potential in this area to do a much more effective form of shareholder engagement. So to date, we tend to see private engagements and shareholder resolutions that are mainly advisory. Most of those resolutions don't pass. Even if they pass, the implementation rate is poor. And the implementation rate is basically non-existent for anything that goes beyond disclosure. And I've also looked at the evidence around disclosure, and it's just not convincingly associated with improvements in environmental performance. So disclosure alone is not going to get us where we go. And that happens to be the stated goal of much of the shareholder engagement that happens right now, both the private shareholder engagement and through shareholder resolutions. So what do we do instead? Well, if you are a shareholder, you have a very cheap and powerful tool, which is that you can vote against the re-election of board members. And although it's a spiky thing to do, it's associated with a much more reliable set of outcomes. You don't even have to win the vote because it's kind of an embarrassment to a board member to lose even a few percentage points of votes in favor. And if you get 10% of shareholders to vote against a board director, it really does make the entire board sit up and take notice, and you're much more likely to see results. This is based on the studies that have been run on shareholder engagement to date. The other thing that you can do is to exclude or threaten to exclude a company from an index, because again, that has to do more with public shaming. No company wants to be on that list of excluded companies, and you tend to see kind of a scrambling to comply with the terms of the index to get back in. And this has been suggested in 2 studies of FTSE for Good indices, so indices that are particularly looking at responsible investment kind of labels for companies. So if you put all this together, you have a very clear picture of where you need to focus. It's really a debt story. Public equity is not where we need to worry about which things you own. Arguably, you could say we should maintain shareholdings in all companies that we have a problem with so that we can vote against their board of directors. And in other asset classes, that's where we should have exclusions in place. And that's kind of a much more complicated story than you normally hear about. But in fact, if you look at the list of major institutions that have divested from fossil fuels, a very large number of them have not actually divested across those other asset classes. They've only divested for the shares. So in a way, it's sort of the inverse of what you might hope for in terms of having an actual impact on the flow of new capital into fossil fuels. And again, why this is important is that it's really with the building of new fossil fuel infrastructure that we see avoidable carbon lock-in. And that's really what needs to change now, because it's once something is built, once the resources have gone into establishing it in the first place, the economics no longer works so well to compete with renewable options. So that's why it's absolutely critical to have a real lens in place in terms of the construction of new fossil fuel infrastructure, especially pipelines and coal and gas powered plants. So happy to take any questions that you may have.
Thank you very much, Ellen. That was very interesting. A few questions just coming in right away. So Sean Fitzgerald asks, as you say, divestment in equities is a positioning move. What if we saw a real shift in the views of purchasers of bonds or the willingness of banks as a result of positioning for their own investors to lend to fossil fuel companies? How can we as a wider society affect this?
I love this question, Sean, obviously. There's already evidence to suggest that even to the extent to which people have been divesting from their bond portfolio or putting pressure on banks, it's already affected the cost of capital for companies, as in it is slightly more expensive for them to borrow money now, even with the limited activity that we've seen thus far. And I think that what we need to do as individuals is to look at where the large blocks of capital that we have a relationship to are. And for us, that's our pension funds. Those are the biggest blocks of capital. And of course, we're at a university with the combined largest endowment in Europe. So that's also important, although I now trust that there's a lot going on at the university to take into account these considerations. But yeah, great question.
Thanks, Ellen. Another question here from Dama Menon, saying you're correct that PRI, TCFD, etc. are more focused on disclosure and action on the risk side. My question is on the new money, particularly on the banking side. Perception is that there is not enough focus on the opportunity side, for example, in support of new breakthrough technologies. What can be done to accelerate capital flow to this part?
Another great question. One thing to just highlight is that we can build all the solar panels we want, but if we don't halt fossil fuel financing, we're still stuffed, because that's where new emissions come from. So, I think we see a lot of greenwashing with banks in particular, highlighting how much green lending they're doing. That doesn't matter if they're continuing to lend to fossil fuels. So Barclays being the top financer of fossil fuels in Europe. They also do a fair bit of green lending, but it's not enough to counteract what they're doing. But on the venture side, I think that is absolutely critical, and it's a real challenge with the uncertainty around new technologies. This is where entities like Cambridge Enterprise at Cambridge are actually quite important, because they do a pretty good job of assessing the feasibility of these projects and doing kind of the soft work to get to them to an investable state. But I think there also just naturally has to be a lot of government support, and there's kind of no way around it to get early technologies off the ground.
Great, thanks, Ellen. There's a few more really interesting questions here for you in the Q&A, and another one just come in, but in the interest of time, we're going to have to move on to our next speaker. So I'll ask you to please type the answers to those questions in the Q&A box. And I'm sorry to have to cut this short, but otherwise we're going to run out of time later. So our next speaker is James Weber from the Department of Chemistry. James, over to you, and please share your screen. And
Is that visible?
yeah, we can see that. It's all
Great.
Good.
Cool. So good afternoon, everybody. I'm a atmospheric chemist, PhD student working in the same group as Paul, and thankfully he's covered some of the topics, things like radiative forcing that I was going to talk about. So that's great. Makes it a bit more familiar. Anyway, so what we've been doing over the last year or so, 9 months, is looking at how changes to emissions from the COVID-19 pandemic may have affected climate. And this work was conceived about a year ago, or sort of 11 months ago. So quite rough estimates for emissions changes, but it's turned out to be reasonably accurate in certain areas. So you probably will have seen headlines like this. Top one, I think it's from BBC, again, all back in sort of April, May last year, wondering how big an effect COVID would have on the environment. And images like this one here taken in Delhi. So on the left-hand side, we've got sort of pre-pandemic, terrible air pollution from traffic, industry, crop burning and things like that. And then on the right, significantly improved air pollution. Air pollution and climate change are sort of linked things, but they are quite necessarily different. And we're more interested, at least in this study, in terms of climate change. But it's showing you that big things were indeed happening. So we haven't looked at in our study CO2 directly, but I'd be remiss to miss out two important studies that did look at CO2. So the top one from Corinne Lequeri at UEA, published in April of last year, made an estimation, and this is again, not knowing how long these lockdowns would go on, that during the first peak lockdown, we were seeing a reduction of sort of 17 to 25% in terms of in global emissions of CO2, and projected to the year, that would be 3 to 7%. 7 to 25% is probably reasonably accurate, but the 3 to 7% over the whole year probably is less so, because of course we didn't foresee quite the sort of extent that the pandemic went on for. The second one from Piers Forster's group in Leeds looked at running a very simple climate model and estimating the change from CO2 and other things. And they simulated a cooling of about 1/100th of a degree, so very, very small indeed. Our interests, as Paul has mentioned, are other reactive gases or species in the atmosphere. And we looked at NOx, sulfur dioxide, which is formed from coal burning, and black carbon formed from burning sort of heavy fuels. The picture on the left here shows the NOx column, i.e. how much NOx there is, or NO2, sorry, from the surface up to the top of the atmosphere over a particular piece of land. And you can see that the one taken in January, we have significant NOx over the Po Valley, where there's a lot of industry, and in parts of Central and Western Europe. And then in the middle of the first pandemic in March of last year, we see it's greatly reduced. So we really know that these chemicals which do affect atmospheric chemistry were changing quite significantly. So as Paul mentioned, we run climate models, and just to give you a very brief overview of what a climate model is, we split the atmosphere up into about 10 million boxes, at least in the Met Office model that we use. And in each box, we simulate wind, chemistry, rain, all sorts of things over a particular time step, normally an hour. And then we reset the model and pass everything to adjacent boxes, and we emit chemicals into the lowest layer. And so to give you an idea of the scale, a grid box over the equator is probably the size of a small country. So it's really not great for sort of individual cities, but it does give us a whole climate view. Obviously, we really didn't know a huge deal about the changes to emissions that were going to happen. So we made some estimations, and we reduced emissions from transport, aircraft, and industry, which are predominantly NOx, SO2, sulfur dioxide, and black carbon, by between 50 and 25%. We looked at 4 different scenarios and a control, i.e. no lockdown. And we chose A2, this scenario here, probably as the most realistic scenario. I should stress that we're not changing CO2 because that's a slightly different sort of a task in our model. And the change to CO2, as Forster's group showed, was probably very small over the short time span of a few months. Oh, sorry. So in terms of ozone, you may have probably would have heard about it, and it's worth differentiating between two areas of ozone in the atmosphere. In the high atmosphere, we have the ozone layer, which is the sort of things that CFCs and aerosols damaged. And up there, ozone is very useful. It absorbs harmful radiation. So we want it high up. Lower down in the atmosphere, in what we call the troposphere, ozone is problematic. It is toxic to life and a greenhouse gas. And everything that we were doing in terms of these changes to emissions would have been affecting the troposphere, and stuff really wouldn't have got into the stratosphere very quickly. So overall, we actually saw a reduction in ozone, or the amount of ozone in the troposphere, which is notionally a good thing. And you can see our various scenarios here. Our emissions kicked in mid-February, and we can see that we saw quite a short reduction, a quick reduction, quite responsive. But then when our emissions started to ramp back up again, and we were assuming that things would be back to normal in mid-June, if only that had been the case, things are pretty much back to normal very soon after emissions return to normal. The impact of NOx, is the key driver here. NOx is produced by emissions from industry and transport, and NOx typically makes ozone. We could also look at where this ozone is changing, and over most of the surface of the globe, we saw a reduction in ozone, which is generally a good thing for air quality purposes. But 2 areas of interest, Western Europe and China, where we saw increases in ozone, which can really which really highlights interesting or different chemical environments, which need to be considered for an air quality perspective when we try and change any sort of emissions. In terms of a vertical sort of slice of the atmosphere, this top plot here shows how ozone changed. We've sort of taken a slice of the atmosphere from the South Pole to the North Pole. We can see that the majority of ozone is changing in the Northern Hemisphere because that's where emissions are greatest, or the change of emissions are greatest, sorry. And it's always worth considering how accurate our modeling studies are. And this is a plot down here from a different researcher from Steinbrecher et al. Recently published, which shows that despite our quite crude approximations, our emissions reductions did quite a good job. We're in red here, and these are the blue lines are the sort of, these are the median and the IQR of Northern Hemisphere observations. So we're doing quite a good job up to about sort of 8-10 kilometers, which is quite pleasing given the speed of which we chose these emission reductions. So the other thing we looked at, as well as ozone, was aerosol. And aerosol are tiny particles in the atmosphere, and they can do some interesting things depending on their chemical composition and size. Sulfate aerosols, again produced by coal burning, actually cool the atmosphere, paradoxically, because they reflect radiation back into space. And that's what we call scattering aerosols on the left here. Black carbon aerosols, on the other hand, produced by sort of heavy industry burning fuels and things like that, do the opposite. They trap energy into the atmosphere and act a bit like a greenhouse gas. So we've got this kind of balance of what's going to happen, which one of these effects will win. And we see interesting regional effects rather than a global picture. Here I'm showing a radiative forcing plot, a bit like Paul showed in his work, and we're really considering how much energy is coming into the atmosphere and how much energy is going out. Obviously, if we've got more going in than out, we're going to see a walling effect, and vice versa if we've got more going out. I just want to highlight 2 areas of interest. The first is over China, where we simulated the greatest absolute reduction in SO2 emissions, because that's where we have the greatest total amount of SO2 due to the industry and the perhaps less strict emission policies they have there. Now, if we reduce SO2, we get less sulfate aerosol and therefore less cooling. So we see a warming in this area here. Over the Middle East, we simulated quite a significant reduction in black carbon. There is quite a lot of heavy industry, oil refining there. But there's a more interesting thing going on. Over the Middle East, we're replacing a very absorbing aerosol, a very dark aerosol, with highly reflective sand. So if we remove the highly absorbing aerosol, we reflect a lot more radiation back into space. So we see a significant cooling. Overall, though, globally, the effect of this aerosol cooling is absolutely minimal, 3 orders of magnitude smaller than the roughly 2 watts per meter squared averaged over the whole Earth we've caused due to greenhouse gas emissions since the mid-19th century. So really, to conclude then, reduction in ozone leads to a small cooling, and the reduction in aerosol also leads to a small cooling. But there are some interesting offsetting effects going on here. Reducing sulfur aerosol led to a warming, but reductions in black carbon and ozone are cooling. However, I guess the most important thing is really to say that climate change is still happening, and this has provided very little respite. But on a more positive note, the atmospheric response to local changes in emissions, so China or India or parts of Western Europe, do provide some sort of evidence base for proposed emission changes in future, both for climate change perspective and an air quality perspective, i.e. we have a better idea of how the atmosphere might respond should certain emission changes be put in place. If you are interested, we've got a colleague and I, Scott, wrote a piece in the conversation about this, and this is the associated paper in GRL. Thank you.
Great, thank you very much, James. That was really interesting. And I'd like to invite any questions for James to come up in the Q&A now, if anyone would like to ask James a question. I was going to ask you myself as well, so you looked at this during the first lockdown back in spring. So have you looked at all, or are you planning to look at all at how the subsequent lockdowns have affected it, and whether there was differences between the lockdowns would be interesting as well?
I think the first point to sort of say about that is the response is very rapid. So there's sort of less memory in the system, if you will. So sort of one lockdown and the second lockdown, after a period of three months of normality, would probably be quite similar. And the biggest effect would probably be the background meteorology, whether it's happening in winter or summer. There is a more sort of coordinated model intercomparison project that's ongoing at the moment, which uses better emissions, more accurate in terms of when emissions kicked in. So they kicked in China earlier than in Western Europe and things like that, which is probably the main focus now. But it's it's certainly an interesting thing to model in terms of short lockdowns versus long lockdowns.
Right. Yeah. Great. Thank you very much. I think if anyone has any further questions for James, then please put those in the Q&A, and James can answer by typing answers directly into the Q&A. And we'll move on to our next talk for today, which is Michael Glerum from the Department of Engineering. So speaking about the production of advanced carbon nanomaterials. So Michael, over to you.
Hi everyone, hopefully you can see me and hear me.
We can, yeah.
So today I'll be talking about the production of advanced carbon nanomaterials from fugitive methane emissions. So a quick overview of the presentation. First, I'll introduce where methane emissions come from and some of the applications of carbon nanomaterials, as well as talking about some of the synthesis techniques for the production of hydrogen or advanced carbon from these fugitive methane emissions. I'll then move on to what the advanced carbon applications and manufacturing synthesis technique is and the network itself, as well as ACAM's future directions and some concluding statements. So methane sources and methane emissions. These are a serious major cause of concern, as particularly the methane emissions have a 30 times higher global warming potential than carbon dioxide. Now, there are several sources of methane emissions from anthropogenic sources, such as landfill sites and farming. However, there's also becoming an increasingly larger issue as well with the melting polar ice caps from Arctic deposits. There actually already exist several innovative manufacturing solutions that can transform escaping methane emissions into solid carbon materials and fuels, but that currently those solid carbon materials are not environmentally or economically sustainable, and they're not relevant enough on an industrial scale. So with the current process of methane activity, what we do by burning it, for example, is we produce 50 gigajoules of energy from 1 ton of methane, but in addition to that, we lock up that carbon as waste carbon in the production of carbon dioxide. What we're proposing is that we're able to provide a solution to this method by reforming that 1 ton of methane in not only providing a clean source of fuel for energy through the production of hydrogen, but also a value in the carbon material as well. So why do we care about carbon materials in the first place? Well, there are a number of different applications of carbon material, of advanced carbon nanomaterials, and the one that I'm particularly going to focus on today are carbon nanotubes themselves. So intrinsically, at the nanoscale, carbon nanotubes have by far and large superior properties than any other manufacturing material that we have in the country today. However, as you get to the macro scale, there are serious problems occurring in the arrangement of that material on the macro scale, resulting in the fact of these properties decreasing. However, over a number of years of research, we've actually managed to be able to surpass what are currently used in manufacturing materials, such as carbon fiber, and, for example, the electrical conductivity of the material and the thermal conductivity of the material. And carbon nanotube fibers are now also able to surpass copper in their strength, their elastic modulus, and also their thermal conductivity, with the added benefit that the species volume is reduced in comparison to both of these materials. Not only are the properties of the carbon nanotubes in a macro scale being able to surpass those of commonly used manufacturing materials, but also they have a lower CO2 intensity of production. However, currently the problems really come from the intensity of the production. So we're right now experiencing the fact that we can only produce these carbon nanotubes at very low volumes and incredibly high costs, meaning that the applications that they can only be put into are also in this remit of low volume and high cost. However, as we're able to improve the intensity of the production, we're not only able to access the higher volume and low cost applications, such as structural applications or in the automotive and aerospace industry, but on the back of that, we're able to increase our hydrogen production and overall lower the carbon dioxide intensity in the manufacturing sector. So methane reformation can be prioritized in two different ways. From methane, one can either focus on producing solely hydrogen at high quantities and high qualities. And for example, an industrial process that actually does this right now is steam methane reforming. However, this process is both energy intensive and produces vast amounts of CO2. And despite the fact that 85% of that CO2 can actually be sequestered, it still leads to an environmentally unsustainable way of reforming methane. So one solution has been worked in at the University of California in Santa Barbara, where they reformed methane over a metal catalyst and produced hydrogen at a 90% efficiency. But here, really, the process was focusing on just a large volume of hydrogen production, where the carbon that was coming off it really had almost no use apart from in soil remediation. Now, as well, you can see this in the plasma from the high rock process, where again, the carbon deposits are of low quality and low yield. However, the hydrogen production is primarily focused on. What we're able to do in Cambridge, however, is focus on the carbon production itself. So we focus on producing high quality, high yield of solid carbon materials. We produced carbon nanotubes on a scale that are able to form macroscopic materials. And the carbon nanotube aerogel, which is the process of what we produce, we're able to make either fibers, mats, or foams. Now, these also can be put into plastic and metallic and ceramic composites, which expose them to a huge range of applications. And really, the material's limitations right now are due to the intensity of its production. So I'll move on to what we actually use in Cambridge in a part of the ACAM process, which is known as the floating catalyst chemical vapor deposition process. What we put into the front of the reactor is iron and sulfur, which is our catalyst and our catalyst promoter respectively. And we also put in methane, which is our carbon source. And this is all under a hydrogen environment. Now, the hydrogen has several roles in this reaction, including inducing the radical catalyzation of methane breakdown into C1 and C2 radicals, which are the crucial intermediary species for carbon nanotube formation. Now, the reactor comes in three separate temperature sequences. There's an initial rise, a plateau, and then a decrease in that temperature. Upon the rise of that plateau, we get the breakdown of our catalyst species, which is our iron and our sulfur. And these initially form a nuclear aerosol particles within the reactor that are able to act as a surface for the production of nanotubes. However, this is actually the wrong point in time because the methane is only able to break down in the plateau points of the reactor's set point, because this is where the initiations of the radical catalyzed breakdown of methane and the pyrolysis breakdown of methane occurs. We then have the decrease in the temperature profile of the reactor, where the iron and the sulfur particles renucleate to form a catalyst surface. And this, of course, enables us to nucleate a little carbon shell onto those catalyst particles. And the carbon nanotubes are able to grow from it. And they grow at such a high concentration and such a large amount that effectively under collision dynamics, these then all the carbon nanotubes can bundle together. And the bundles under van der Waals forces then form a macroscopic material, which we retrieve out of the reactor. Now, on the bottom of your screen, you can see some typical images of what we see in real life for the reactor, where we have a macroscopic material. And if one was to look under the electron microscope at 1 micrometer, you would see all these bundled different materials that are interwoven together. On the nanoscale, you take it down further, you can really see this material is made out of individual carbon nanotubes that have come together, reducing the surface energy and producing an under van der Waals forces. So this is really a nanomaterial that is able to form a mesoscale structure which can be retrieved as a macroscopic material. However, the complexity of this reaction should be noted, because this is a highly complex reactor, and producing these materials on a large industrial scale actually requires incredibly large reactors in itself. So industrial bodies have several metrics that they examine the technical feasibility of a catalytic process before taking it on. And these include things like reactor yield, product concentration, the ratio of the product to catalyst cost, and finally the catalyst selectivity. So really and truly, the FCCVD process that I've mentioned before you actually really lacks in the reactor yield and the catalyst selectivity. The problems really come from the fact that the reactor yield is incredibly limited due to the fact that you have two zones where the catalyst has to nucleate, and also there's a severe loss on, and the methane contributions are different as well. So even though the product, so we're definitely subpar on the reactor yield. On the product concentration, it's not so much of a problem that we're below subpar in industry ranges, and this is primarily because the product can be easily separated out from its byproducts, which is gaseous hydrogen, and the product itself can be used, is a solid. The product to catalyst cost ratio is excellent because effectively the catalyst can be anything from iron shavings to rust. The catalyst selectivity, though, however, is a major cause for concern. And ultimately, this is what many groups in the world are focusing on the production of very good catalyst selectivity. Now, my research focuses on primarily looking at the reactor yield. Now, one way of improving the reactor yield is by firstly limiting the complexity of the reaction in itself, but also improving the reactor energy density. One way I'm able to do this is by proposing a pseudo-packed bed reactor in which we have a packed bed of inert particles over which we pass over our hydrogen and methane. The hydrogen and methane is then able to break down over the top of this packed bed. And by able to control the temperature gradient, we're able then to control the exact point at which this breakdown of methane occurs. We're then able to deliver the iron and sulfur catalyst to the exact point of this nucleation in order for them to nucleate and form the aerosol particles, which ultimately can produce the carbon nanotube aerogel.
Michael, I'm gonna have to stop you soon because it's running out of time. Do you want to finish up?
Sorry, quickly? I was just going to quickly say, just including remarks on the statements. And essentially the methane emissions can be controlled. However, there has to be an improvement upon the improvement of incentive for these purposes. And then also the fact that we are able to reform methane into a valuable carbon product. However, there must be significant improvements in that. So yeah, thank you very much, and sorry for overrunning.
That's all right. Thank you very much. I mean, it's an extremely interesting talk. There's a question for you who's come in the Q&A here, but I'm going to ask you to type an answer, please, just in the interest of time.
Sure.
A question from Sean Fitzgerald there. And we'll move straight on to our final speaker today, which is Sam Gabra from Chemical Engineering and Biotechnology. So Sam, over to you.
Firstly, thank you very much, Eric, for moderating such various topics. And I'd like to thank all of the audience now for staying until the very last topic. And I hope this won't be a very boring end for any of our audience. I'm just trying to share my screen now.
Sure, yeah, go ahead.
Can you see my screen now?
Yeah, we can see it. All good.
Okay, wonderful. So now I would like to speak to you about the chemicals production and whether it can be more environmentally friendly. This would be a bit of a smooth transition from the earlier talk of Eva. And this is from the Department of Chemical Engineering, and it's co-funded by Johnson Matthey, and it's an EPSRC case. So what's the problem? The problem is that the value-added chemicals that we need in our daily life, like ethylene and ethylene oxide, which we use for polymers production, antifreeze, and many other products, is one of the main causes for emissions and for climate change. So how this happens is that we feed in some hydrocarbon into a reactor to produce such chemicals, but in general, we need the co-feeding of oxygen into such a reactor for the production of such chemicals, which leads to the unfortunate production of carbon dioxide. Not only this, the problem as well is that having oxygen and a flammable hydrocarbon would lead to a flammable mixture that we need to feed in some nitrogen to dilute the whole reactor. This means that carbon dioxide is dilute, making the capture of it and storing it very expensive and would lead to a lot of process steps. Unfortunately, renewables cannot help much for such a problem because the main problem is the chemical feed into the reactor rather than the source of electricity that we are using, which means that we need to propose different approaches for such a problem. One of these approaches is chemical looping, which we are proposing. And this was mentioned earlier in the talk of Eva, so I'll not dwell much on this, but the main idea is that we are only capturing oxygen without nitrogen so that we would feed in pure oxygen to the reaction to produce our value-added chemicals in a safer, more selective, and more intensive way. So we went to see whether we can apply such chemical looping for the production of value-added chemicals. The first step was to identify whether chemical looping can ever be feasible for such a process, to see whether there would be any economic advantage for it or also any process benefits. If it turned out to be potentially feasible, then we would go into the development of a catalyst to make the whole process technically, economically, and from a process perspective feasible. The two processes we focused on is the ethane ODH, or the production of ethylene, which I'll explain now, and the production of ethylene oxide, which I'll explain later in the presentation. So, as most of you might know, ethylene is an important chemical that's being produced now by the thermal cracking of the ethylene molecule, of the ethane molecule into ethylene and hydrogen. But unfortunately, the current process requires a lot of energy since the reaction itself is endothermic, meaning that it requires energy to be fed for this reaction to proceed, and also limited by thermodynamic equilibrium. Another process has been proposed, which is the oxidative dehydrogenation of ethane, which means that we are feeding oxygen to ethane to produce ethylene and water, with this reaction being exothermic. The main problem for such a process is that, again, we have a feed of oxygen and the flammable hydrocarbon, leading to a flammable mixture and the cost of separating oxygen from nitrogen in air. So what we are trying to propose here is having a chemical looping ODH process as an alternative. We went to explore the techno-economics and the process benefits, and we found out that chemical looping ODH can offer both savings with respect to the raw material that can be used for the process, as well as significant savings with respect to the energy consumption, which led to the next step, which is developing a catalyst for such process. We tried to prepare a catalyst made of some precious metals like molybdenum, vanadium, niobium, and tellurium to make the process feasible at low temperatures. And depending on the preparation conditions, we had multiple phases of the different metals that we have. One of the key phases is a phase which is M1 phase, which is catalytically active for the conversion of ethane to ethylene. Other phases are thought to be inactive, meaning that we wanted to maximize the percentage of the M1 phase, which is catalytically active. The catalytic investigation showed that we can have a catalyst which is both stable across multiple cycles. We can have the catalyst at very high selectivity towards ethylene and with very significant conversion to ethylene, meaning that experimentally and from a process perspective, the ethane ODH is a feasible process that we can take further. Another process is the ethylene epoxidation to ethylene oxide. Again, ethylene oxide is a very important chemical that's used for the production of polymers and for biological sterilization, for surgical equipment, for example. Conventionally, or in the industry at the moment, we produce ethylene oxide by the feeding of oxygen and ethylene on top of a silver catalyst. And we have the two reactions here, where the first is the production of ethylene oxide, and the second is the unselective or the undesired reaction, which is the combustion of ethylene to carbon dioxide, where we try to maximize selectivity, meaning that we try to maximize the percentage of ethylene oxide in the product stream, and we also try to maximize the conversion, which is the amount of ethylene converted in the reactor. We went to look at the process, and we found out that chemical looping can only introduce minimal changes to the process, but such minimal changes, which is mainly in the upstream part, the reactor part, that chemical looping can introduce significant cost savings, since we no longer need purified oxygen, and definitely enhanced safety because there is no mixing of oxygen and ethylene. And finally, minimal changes to the process because we will only change small part of the whole equipment. We went to do the economic and sensitivity and scenario analyses for such a process, and we found out that if we increased the selectivity of chemical looping catalyst more than 76%, we would be able to even double the net present value of the whole process, meaning that we would also gain an economic advantage from such a process, given that all of the other factors constant, and the conventional process here is at 85% selectivity. So even at lower selectivity from our novel process, we can still yield a significant economic advantage from chemical looping. So can we have a catalyst for such a process? This is the next question. So this is a concept for the catalyst that we are using now, where we have a core of strontium ferrite, which acts as an oxygen carrier that provides oxygen to the silver on top that can catalyze the reaction. What we went on to do is to develop this catalyst more, to have it more effective with respect to selectivity and conversion. And this was achieved through three main aspects. These are the oxygen properties of the carrier itself, the catalyst carrier contact, and finally the catalytic properties of silver on top. For the sake of time, I'd only focus on only two aspects. One of them is the oxygen properties of the carrier. So we were able to merge two perovskite structures of the catalyst. One of them is the cubic strontium ferrite, and the other is rhodesium copper phase, by simply mechanically mixing them. And we found that we can get different ratios of the two perovskites. And if we put these into the oxygen carrier, we would have a huge advantage in terms of the yield, where we can have 4 times as much ethylene oxide as before. Another is the catalytic properties of silver, and we were able to reach selectivities up to 80% if we only increased the percentage of the loading of the silver on top of the oxygen carrier to 30% compared to only 15%, which was the initial stage that we started with. And this 80% is much higher than the 76% benchmark that we already mentioned, and we are in our way to have higher selectivities in the future. So as a conclusion, this means that chemical looping is attractive for both processes, and it doesn't only offer an environmental saving with respect to the carbon capture, but it also offers significant financial savings that would make it very attractive to be applied industrially. We were able to develop 2 effective catalysts for both processes, meaning that on an experimental level, these 2 processes seems to be very successful. The next steps should be on modifying the catalyst to have better performance, scaling up the 2 processes, and then hopefully adopting them industrially. So thank you very much, and I'm very happy to answer any question of yours.
Thank you very much, Sam, for a very interesting talk. And I'm sorry you ended up right at the end there, but thanks for sticking with us, everyone. And I mean, I was just going to ask a very quick question myself. I mean, you know, obviously say that scaling up is the next step here, or one of the next steps. Is there something you've looked into with your lab, or are looking into how to scale this up?
So we currently have an experimental setup that has a bigger capacity than the ones that were used for these experimental investigations. So we are in our way to have more amount of catalyst and see the sustainability of such catalyst across many cycles to be applied industrially. So yeah.
Okay, great. Well, keep us posted on the advancements there, and it sounds really interesting.
Yes, thank you.
Thank you. If anyone has any other questions for Sam, then now quickly put your questions in the Q&A, please, before we end for today. And I will just very quickly still share my screen where I've got the following events that are coming up this week, where you can join us for more interesting discussions. So we've got, here we go. Tomorrow, there's the Climate Change Lecture Series coming up, the first installment of the Climate Change Lecture Series 2021 on human well-being, justice, climate action, and the road to COP26. So please do sign up for that at climateseries.com. And on Friday, Energy Transitions are holding their next discussion series on photovoltaics, which I think may also be of interest to many people here. And then we've got various events during the Cambridge festivals at the end of March, so please do join us as well. And a final reminder for the deadline today for submissions to Climate Expo, the virtual conference, which is still open today. So please do consider those things and join our mailing list and Twitter and LinkedIn as well. And with that, I would like to end for today. And thank all our speakers for some great presentations, and there was a really great variety of different topics today, but it was interesting to explore all the connections between these topics. So I'd like to thank you all very much.